Hello, everyone. This is Mr. Haberly. Still not feeling great. You might hear that in my voice. Um, I'm going to be out again today, and so what I wanted to do is take some time and go through the very last thing I need to talk about in the forces unit, so that way you can have a test before Christmas break. Now, um, here's the first question. Which type of tires will give you a better grip on the road? Now, you should have a Peardeck to follow along with me as I go through some of these slides in regard to friction. Okay, so make sure you have the Peardeck open. You should be able to have a slot to put your answer to this question. Which tire do you think would give you the best grip on the road? Now, when I ask a question like that, it might make sense to pause the video to make sure that you have time to answer the question, and then you can play it again as soon as as soon as you're ready for me to continue explaining. But let me just start. So, a lot of people might say this one because it looks newer and it doesn't have as much wear and tear on it. Well, this one is certainly wider, and so a lot of people might have picked this one just because it is wider. But the truth of the matter is that friction doesn't matter about how wide things are or even how worn out they are. Friction depends on what the material they're made of, and since they're both rubber, um, technically they should provide the same amount of friction. Now, obviously, you really would prefer something with better treads in the winter time, but that's because driving in the winter has a lot more complicated things than just friction. Friction is actually a pretty simple idea, but is it a good thing or a bad thing? Go ahead and answer that question in your Pear Deck now. Now, a lot of people might say that it's specifically a bad thing because we talk about it in terms of it always slowing things down, especially when we're talking about sports. Like if there was no friction, we'd be able to run faster and throw things further. But think about a world without friction. Um, None of the cars would work. In fact, none of the cars could be parked. They would slide to whichever was the lowest part of the parking lot. No one could walk anywhere. Think about how you have friction and contact with the ground. Friction is responsible for you being able to stand upright. So, 24 hours without friction would probably be the end of humanity as we know it. So, what would happen if you and all friction was turned off for the rest of the day? Well, you would probably not make it home, near would everybody else. Cars wouldn't be able to go anywhere. Friction is actually a very important thing to our day to day life. Now, here's an interesting one. How do you walk? What are the forces acting on you? Okay. Oh, where's my picture? Sorry, guys. Behind the scenes look. I wanted this one. Great. Yes, so when you're walking on the ground, you have your weight force, obviously, that represents by this arrow here. Okay. And then you have your normal force, this arrow going up like this. Okay. And then you have this force from you pushing your foot backwards. If you don't believe me, take a second to stand up and walk a couple steps. You're not pushing yourself forward when you walk, you're actually pushing the ground backward. And since you push the ground backward with this blue arrow here, friction is actually an equal and opposite force that pushes you forward. So even though you might have known you need friction to walk, I think it might be and not an exaggeration for you to realize just how vital it is to the fact that it's what's actually pushing you forward. Same with like a car moving on the road. The tire turns and pushes the ground backward so that the friction force can push the car forward. So it's interesting how friction is super vital to the things we need every day. But what is friction? Well, friction is the force that resists one object from sliding against another. So, direct motion or attempted motion. So basically, you have this box on the surface and it's trying to move. And even though the box and the surface might appear smooth, if you zoomed in to like a microscopic level, you would find that it's actually both extremely rough surfaces. And this doesn't really matter what the materials are made of, no matter how far you zoom in, there's going to be a certain amount of bumpiness or ruffiness down at this microscopic level. And these things are going to interlock, kind of like teeth of a comb, like having two combs connect to each other. Okay. And so basically, it's these bumps rubbing against each other, which causes the friction force that we experience. Now, if you're trying to pull a couch, the only thing that resists you is the force of friction. What are some things you can do to make it harder? So take a second, answer this question in your Peardeck. What are some things you can do to make it harder to pull? Okay, so one thing I'm hoping people suggested was you sit on the couch, like having a friend or two sit on top of the couch or stacking large heavy things on top of the couch would certainly make it harder to pull. Another thing you can do is you could actually take the carpet that the couch is on or the floor and move it onto something that's more frictionful, like say like a rubber mat or something that really wouldn't let it slide very much. Okay. So there's two things you could really do. You can add stuff to the top of the couch, or you can change the surface that the couch is applied to. All other options probably would not work, but if you have one you think would work, let me know when I come back to school. Okay. Now this is where the couch question factors in to the force of friction equation that you guys have on your reference table. So if you look at the back of your reference table, you'll have this equation. Force of friction is equal to the coefficient of friction times the normal force. Like that's the whole thing. Okay. And so this basically is a visual or a mathematical representation of the couch question. Force of friction only depends on two things. One is how sticky or how much grip the two surfaces have. So like I said, when you're trying to make the couch harder to slide, one thing you can do is you could put the couch on a more sticky surface, something with a higher coefficient of friction. So this U that's drawn pretty weird here, it's called mu, like the Pokemon. This is the coefficient of friction, and it represents how sticky the two surfaces are together. Okay. And the coefficient of friction is different depending on what the materials are made of. And then there's the normal force on the object. The normal force basically is just the force that's supporting the object, or in our case, the couch, right? If I stack a whole bunch of people on top of this couch, that means I'm increasing the normal force that the floor has to put up in order to support the couch. So that means that if I'm increasing the normal force, I'm also increasing the force of friction. That's because basically, if I have a huge normal force, that means I'm pressing these two surfaces tighter and tighter together, which makes it harder for them to slide apart. So basically, the force of friction is equal to how sticky the two surfaces are multiplied by how tightly they're pressed together. So U times normal force. Let's do a quick example problem. Okay, so I have a pushing force here, and then a friction force. There's an object on a green surface. A 10-kilogram object is sliding on a table, and the coefficient of friction is 0.54. Well, what is the force of friction in the object? So I'm going to ask you to pause in a second and actually solve this problem yourself. But what I'd like you to do is think about, okay, how do I figure out the normal force on this block and then use this coefficient of friction to calculate the rest? So take a second, pause the video, and try to get that answer now. Now, either way, let's take a look at what's happening. So I'm going to throw in a couple more forces here because there's the force of gravity and the normal force, and the normal force is what I'm interested in solving for. So I know that the normal force is going to be equal to gravity because this is a nice flat surface. There's nothing else to really mess this up. So that means the normal force should just be equal to mass times little g. So 10 kilograms times 9.8, I get a normal force that's equal to 98 newtons, which is the same thing as the weight of the block. Okay. Now, if I take this force of friction equation, this brand new one from the reference table, I take the 0.54, which is the U thing, and I multiply it by 9.8 or 98. Sorry, I forgot the 10. 98. And that'll give me a force of friction of 52.92 newtons. Okay, so Friction's actually not that hard to calculate. The hardest part is normally finding the normal force. Okay. What are the units of the coefficient of friction? Oh, have you noticed this? I always tell you guys to include units on your numbers. So 10 kilogram mass, 9.8 meters per second squared, 98 newtons, and 53-ish newtons for the force here. What are my units for the coefficient of friction? I didn't include them. Well, it's actually the first number we've had all year, and probably, I think there might be one more. There are no units, and that's because when you multiply the normal force, which already has units of newtons, by this number, it has to equal another force. It has to equal another thing that's measured in newtons. So whatever I multiply this 98 newtons by, it can't have any units to mess that up. So basically, the coefficient of friction has no units. Okay, so imagine this. Imagine you're pushing something, okay, something really heavy, and if you tried to push like a couch that had a whole bunch of stuff on top of it, my guess is that your first push might not really work, okay? Basically, it would probably not move the first time you push it. So let's say here we have this push, and it wasn't quite hard enough to get it moving, okay? That means that the object is initially still at rest. There's actually a certain point where I have to push it harder and harder and harder and harder until eventually that couch would start sliding. And then I move into an easier level of friction where the couch is actually sliding. And this is kind of a nice visual to represent the two different kinds of friction. We have friction when things are not sliding, we call the static region, and friction where things are sliding, called the kinetic region. Okay, here's a much better visual. So, static friction is friction between two objects that are not sliding whatsoever. Kinetic friction is the friction between two objects that are sliding. Okay, so I've got a cute little GIF here. Okay, now in certain physics questions, you're going to have to be able to tell the difference between whether or not the question is talking about static friction or the question is talking about kinetic friction. And so it's very important to keep in mind which objects are sliding and which ones aren't. So let's do a quick example. So tell me what your answer is for this question. An object's at rest on a ramp, is it static or kinetic friction? Hopefully it didn't take anybody too long on that one. It's static because there's no sliding whatsoever. The block is held up by static friction. Okay, but now we have an object and it's sliding down the ramp. Is it static or kinetic friction? Answer that in Peardeck. Also not too terrible. We have kinetic, but it's not always straightforward. Static is not always clear. Kinetic is pretty much always clear. Let's take a look. A person walking, well, a person walking is definitely moving, but is it sliding? Answer this question in the Peardeck. Is it static friction or kinetic friction? Well, so if you answered this correctly, it is static friction, and that's because there's no sliding between your foot and the ground. Friction does not mean stationary, it just means sliding. So you can have moving objects that are applying friction, but that as long as there's no sliding involved, it's still considered static friction. Let's do another one. Okay, a car driving on a road. So here's a wheel and there's some forces. Here's a friction force acting on the bottom of the wheel. If a wheel is rolling across a surface, is this static or kinetic friction? Answer the question. Let's take a look. Oh, yeah, this one's static too, unless the wheel started slipping, in which case that would be kinetic. But static is what the wheel is because typically when an object's rolling, typically when I'm driving in my car, the wheel maintains solid contact with the road. So therefore, this is, again, static friction. All right. One more question, but in order to answer it, I want to bring your attention to your reference table. This should be on the front page of your reference table, and it is a fantastic piece of information is extremely useful to us. This is the table of approximate coefficients of friction. Okay, so we've got rubber and concrete, rubber on concrete for dry and for wet conditions, rubber on asphalt for dry and wet conditions. I wonder why these are such important information. Well, that's because driving is a big deal when it comes to friction. Driving on the road is actually the #1 concern. Rubber on ice, waxed ski on snow, wood on wood, steel on steel, copper on steel, Teflon on Teflon. Now, this is a chart that tells you how strong friction is going to be or how sticky the two surfaces are going to be if they're sliding against each other, or in the case of static friction, are stuck together. Okay. Now, what do you notice is that is different between the kinetic and static friction coefficients? Well, one thing I notice is that the kinetic frictions are all smaller than the static frictions. You guys see this? So the static frictions are all larger than their kinetic counterparts. Okay. What are the units of the coefficient? Oh, we already went through this. There are no units, so they don't list any. So there's no units for these numbers. You should be able to find this table on the front page of your reference table. And so this is an important idea because basically you can come to this reference square in questions where they don't give you the coefficient of friction. So for example, a waxed ski is sliding across a snowy path. What is the coefficient of friction between the ski and the snow? Okay, well, in order to figure this out, you go to your reference table. So answer this question in your Peardeck by finding the answer on your reference table. Okay, so wax ski on snow, like we said, has a coefficient of friction of either 0.05 or 0.14. And so the difference is this static friction or kinetic friction? Well, it mentions that we're sliding, so that means we have to pick the kinetic option. So it is 0.05. There's no units, so 0.05 is just the coefficient of friction. Okay. So to end the video, let's talk about what that frictional force would be. So if this person weighed 550 newtons, then what is the force of kinetic friction? So if this is the weight, and we'll assume it's on flat ground, even though I know it's probably slanted, calculate what the force of friction would be in this situation. So I'm going to say that the normal force is equal to the weight of the person, simplifying this problem a little bit, right? And so then I take the friction equation we talked about earlier. We set it equal to 0.05 times that normal force, and I get 27.5 newtons is my force of friction, which is not a whole lot of friction considering how big the person is. So that's friction, the basics. I hope to go over it more with you when I'm back in school. If you guys have any questions, please send me a message or let me know. Otherwise, guys, have a great day. I'll see you soon.